Okay, ladies and gentlemen, welcome to this sixth edition of the Battery Tuesday today. I'll quickly recall that we already had several Battery Tuesdays this year. We already had also one thermal workshop, and we are now at this, it's the seventh edition of the Battery Tuesday with a presentation by LEM, by Emil Namor, which I'm going to introduce right afterwards. But before I do that, I just wanted to highlight that we are having another 3 Battery Tuesdays that are coming up, October, November, and December. And we are also having a workshop on lithium metal batteries. Registration for this workshop is already open. That is going to happen on the 5th of October. And we are having the annual conference that is scheduled for the 23rd of November. The program is not yet completely finalized. We're still waiting for 1 or 2 speakers, but we'll announce that pretty soon. And you're already invited today to look at the program and to also get the date at least reserved for this event. Now, I'm happy to introduce you to Emil Namor, who is Senior Electronics Engineer at LEM. LEM is a world supplier for current sensors. Current sensors are very important elements in battery management systems. Especially the accuracy of current sensors is very important to also give good state estimates. And in this domain, LEM has a good offering, and I'm happy to introduce you to Emil, who will present us an overview of the company and then giving us a deeper dive into the current sensors that they have today and also the trends that are seen on LEM side. Emil, the floor is yours.
Thank you, Andreas. So I'll share my screen right now. Please let me know when you see the presentation. Okay,
perfect.
Great. Let me also. Okay. Yeah. So yeah, thank you again, Andreas, and to the iBAT Association for giving me this stage, this opportunity to present LEM and its activity around battery systems. The presentation is titled "Current Measurement for Battery Systems Today and Tomorrow." It is split in 3 main parts. First, I introduce the company in general terms. In the second part, I'll go over the products that we produce and sell for specifically battery systems and BMS. And in the last part, I'll do a more forward-looking discussions about some trends that we've observed and how this relates to electrical measurements. That is how what new requirements might be there for electrical measurements, and how future current sensors might foster these new trends in battery systems. So without further ado, I'll jump into the presentation of the company. So the motto of LEM is leading the world in electrical measurements. You might know us for the Hall effect current sensor that come into the in blue color, which is very typical. But we produce much more, and I'll show you some of this. In terms of size, we are a company of about 1,700 people, distributed in 17 countries, and we have a portfolio that goes from integrated current sensors of a size of a chip to instrumented modules such as energy meters, and we also rely on several different technologies for providing current and voltage an array of electrical measurement, not limited to current. Our headquarters are in Geneva, or in Meran to be precise. We moved there slightly more than 1 year ago, and we have R&D operations as well in France, in Lyon, in Bulgaria, in Sofia, and in Beijing, China. And we have also production sites in both Europe and in Asia. And we have sales branches on basically all over the world, wherever our customers are. This slide gives you an overview of the history of LEM. I won't go through all of it, of course, but just want to point out some relevant milestones. It was founded about 50 years ago, 51. We celebrated last year our 50th anniversary. And at the very beginning, it was selling current sensors for the trams moving in Geneva. A relevant milestone then is 1998, when LEM entered the automotive market, and 2003 when the first sensors for hybrid electric vehicles were sold. Since then, the company grew quite a lot, and in 2021, it got to sell 66 million sensors per year, and the number is still growing. These are numbers just to give a perception of the size of the company. These are numbers related to last fiscal year, for about 400 million Swiss francs in sales, with considerable growth from previous year. And out of these, about 30 million are invested in R&D activities that are covered by about 14% of LEM's workforce. Let's say at the root of the growth of LEM, there is the fact that in the end, our core business is to provide solutions for electrical measurement that fits very well with one of the main mega trends of our societies, that is electrification. So as you surely all know, humankind has a need to reduce CO2 emissions considerably, and it has set ambitious target for 2050 to reduce CO2 emissions in basically all economic sectors, energy production, transportation, in the heavy industry, and basically all around all sectors. LEM is positioned to support this effort by providing products for electrical measurement in a number of very fundamental domains, such as energy efficiency with automation, tracking, and smart grid, the decarbonization of energy production. We provide sensors for renewable energy systems and stationary storage, and as well, and I think this is the most relevant for today's presentation, electrification of transportation, which is today primarily based on battery-powered vehicles. Yeah, this, as I just said, in the end, LEM sensors go in a very wide variety of systems, going from renewable energies, railway, automation, and electrification of transportation, both in electric vehicles and also in the charging infrastructure that supports them. To be a bit more specific and visual, this is a kind of overview of the kind of products that LEM sells. We have more than 2,000 product references coming from more than 240 product families. And these go from, in terms of current measurement, from very low currents in the order of milliamps for applications such as residual current monitoring, to very high currents in the order of tens of kiloamps for applications such as, for instance, megawatt scale electrolysis plant. When it comes to electric vehicles, there are a number of places where our sensors are positioned. Basically, wherever an electrical system needs a current measurement. So, for instance, the high voltage inverter and the electric motor, the 12 volts lead acid batteries that act as starters, where we have products that measure the current, voltage, temperature, and also carry out some state estimation. And as well, of course, the high voltage batteries, which are the let's say the principal element of interest for today. Before jumping into the battery specific products, still a few words about how LEM is evolving. When LEM started in the 70s, the products that we were selling were these very heavy and massive current sensors. We still have a number of products that are quite big, but there is a general trend to have more and more integrated and smaller sensors, and we have a number of product lines today that are basically chip-sized sensor to be integrated in power electronics and all kinds of electrical systems. And this is also driven by new expertises that are being developed within the company. One is ASIC design, and one is embedded software, since more and more software is also being integrated in these sensors that at start were providing an analog output. Today there is more and more intelligence embedded in the sensors. Now, this is for the company as a whole. I would like now to jump into the product lines that we currently have for BMS applications and battery systems. Starting with a very high-level summary. The high voltage batteries, such as those that are used in electric vehicles, is in the end a static assembly of lithium-ion cells connected in parallel and series, assembled into modules and then into a battery pack that is then connected to the rest of the powertrain, that is the inverter and the electric motor. The interface between the battery pack and the inverter is a battery disconnection unit, where a number of components are placed, such as connectors, fuses, and a current sensor. That is what we provide. And the current sensor, as well as the other elements in the BDU and other elements in the battery pack, all communicate with the battery management system. That is the device that monitors the well-functioning of the battery pack, ensures its safety, and computes a number of quantities for optimizing the operation of this battery pack. The current sensor in this system is a small component, but in a way it is a very, very important one, since it provides one of the key quantities to the BMS for its computations. And especially if you think of the state of charge, which is probably the most fundamental quantity that the BMS computes. In its simpler form, it consists in the integration of the value of the current over time, divided by the battery capacity, and this relates in a very explicit manner to the range that a vehicle can provide. So the more accurate the sensor is, the more accurate the state of charge is, and therefore the more accurate the range estimation is. And having an inaccurate sensor means that margins have to be left the battery capacity. Therefore, although this is a small component, in the end it can have quite a relevant impact in the sizing as well as the design of the battery. What you see here is the let's say product lines, except for our newest addition, for which I'll dedicate some words in the following slides. But what's important here is to notice that we have a number of products that are based on different technologies. Our best in class in terms of accuracy is the CAB product line that is based on flux gate technology, and that thanks to this can reach quite high accuracy. Overall accuracy over a range of temperature is 0.5%, and also offset provided on the measurement provided by this sensor is quite low. For some references down to 10 milliamps, which is quite impressive. The other families in this list are based on open loop Hall effect technology, which makes them considerably cheaper, but also a bit less accurate in current measurement. Our newest addition to this family of products is a product family called the HSTBV, which is somehow in between of the very extremely high performing CAB and the slightly less performing but cheaper open loop Hall effect based sensors. This is a product that is still based on open loop Hall effect technology, which makes it quite cheaper than the CB, but has reached a higher accuracy than the other open loop families, reaching 1% accuracy. It comes in different packages, having either one channel, dual channels, or a dual channel based on different technologies. And you see here the name of the ASIC that it integrates. It's the LEM, which is at the core of its improved performance in the open loop technology. This is, as I said, this is let's say the breakthrough with this sensor family is thanks to the ASIC it integrates. There is let's say a long story also in ASIC development for current sensors for battery applications that dates back to 2007, and you see on the right here the improvements that have been reached in sensitivity and offset. So today, thanks to this latest addition, the LEM, we are able, with open loop technology, which is the cheapest Hall effect based technology, achieve performance in the range of 1% sensitivity error and 100 milliamps in offset. Based on this chip, we are also working on different sensor concept for a sensor that sit in the battery junction box primarily in electric vehicles. One is, for instance, a concept mounting two different sensing technologies, Hall effect and shunt, to achieve heterogeneous redundancy, which is desirable for functional safety purposes. And another is what we call multi-point sensing, that is a component that collects in a single device different measurements that are needed in a battery junction box. That is current measurement, a number of voltage and temperature measurements, as well as insulation monitoring. Last point about this new family of current sensors for battery applications. And that also relates to our to the increased focus on embedded software within LEM. This breakthrough or this particularly low offset that this sensor is able to achieve is thanks to software that is embedded in this ASIC that aims at compensating the magnetic offset that the ferromagnetic core of these sensors introduce. And by doing this, we are able to considerably reduce the offset that the measurement of the sensor has, and that is a major element that it must be considered when using a current measurement for a state of charge computation. Now this is it for our current offering in terms of current sensor for battery systems. I would like now to jump into some more forward-looking topic that I've I would say assembled in view of this presentation from some interactions we've had with our customers and that we've observed in evolving industry of battery systems for electric vehicles. The topics I would like to touch here are again state of charge estimation, which relates in a very straightforward way to the current sensor quality, but also battery diagnostic and battery architecture. So I'll start by state of charge estimation. In its more basic form, state of charge estimation is a rather simple computation. It consists in knowing an initial state of charge of a battery and adding to that the integral of the current over time divided by the battery capacity. Of course, there are many subtleties to this. The battery capacity changes in time and also, for instance, with temperature, but the basic principle is rather simple. The drawback of this is that any constant error that affects the current measurement is also integrated, and this introduces a drift in the state of charge computation that can accumulate over time. The slightly more reliable method for state of charge computation is using column counting plus a reset of the state of charge value from time to time based on the relation between open circuit voltage and state of charge. This also remains relatively simple, but requires that a moment where to do this reset based on the open circuit voltage is available, which is not always the case. And also it is challenging in the case, for instance, of LFP batteries that have a very flat OCV curve. More sophisticated methods that we are seeing starting to appear are model-based methods, where an algorithm that is based on an observer, such a Kalman filter, is used together with a model of the battery that is being monitored. This model can be either an equivalent circuit, where an equivalent circuit allows for the prediction of the battery voltage, and this voltage is then compared to the measured one, so to basically correct the state estimate dynamically. A more elaborate version of this is based on physics-based models, where you don't have an equivalent circuit, but rather partial differential equations that model the physical and chemical phenomena that happens within a cell. And by doing this, they also allow for accurate state estimation. The drawback of these methods is that while being potentially very accurate, they also contain models that are potentially very hard to parameterize. A further comment about especially the physics-based model is that I believe is relevant is that the implementation of this in battery management system is not only related to this, the quest for higher accuracy in state of charge estimation, but also by the fact that these allow for further functions, such as, for instance, optimization of the fast charging profile during fast charge, based on quantities that are not observable but estimated, such as, for instance, anode over potential of the batteries. And I think it's rather interesting to see that these methods starts to be applied actually also in the industry. An example being Rimac, the Croatian OEM that implements this method for such purposes. Now, how all of this relates to current measurements? I've assembled here a very rough table just to give an idea of what the effect of offsets on the current sensor means on the range, on the state of charge estimation, therefore on the range of an electric vehicle. For sensors with an offset of 2.5 amps, as was the case some years ago, this effect was very remarkable, and therefore also the margins that one had to leave on the battery size were equally remarkable. Nowadays, offset values are in the range of tens or hundreds of milliamps, and this for a typical application translates into a range accuracy of in the range of hundreds of meters, if to most few kilometers, which is still non-negligible, of course, but it's considerably lower. So this is to say that there is a very classic premise in many battery modeling papers that says that we need better models because column counting causes state of charge drift. I believe this holds true only in some cases. It is, I still firmly believe that we do need much better battery models, but this is not only due to the SOC drift, since with today's accuracy in current measurement, this drift has been brought down considerably. And in many cases, column counting is actually quite a reliable state of charge estimation method. Sorry. So what I've been able to observe with respect to state of charge estimation is that there are in fact new model-based methods that are being more and more used, but this is not only due to quest for higher accuracy in state of charge, but rather by usage of these models for further applications besides state of charge estimation only. And another relevant point is that while for column counting, the relation between sensor accuracy and drift in state of charge estimate is very explicit and straightforward. It is very much so in model-based methods. So this is actually a quite interesting topic or area of research, in my opinion. What is the relation between the accuracy of the sensors and the state estimates in these more complex estimation algorithms. Another topic where current measurements play a major role is battery diagnostic. And there are, of course, many possible approaches to battery diagnostic, but I'll focus especially on one. I would say, unsurprisingly, to those that know me already, that is impedance spectroscopy. Impedance spectroscopy is one of the main method to characterize electrochemical systems, is widely used in laboratories, and there is quite an effort to bring this method also on board of battery systems that sits in electric vehicles. Its principle is shown here. It's of course a complex method, but the principle is rather simple. Consists in exciting an electrochemical system such as a battery with a sinusoidal signal, typically a current, and measuring its response via typically the voltage. Out of these two quantities, one can compute the complex impedance for a given frequency as a ratio of voltage over current. And doing this exercise at various frequencies provides an impedance curve for the electrochemical system under study that can tell quite a lot about its state. For batteries, the typical range of interest in terms of frequencies is about 10 millihertz to 10 kilohertz, and typically the quantities, the impedance values range from fractions of milliohms to few milliohms or few tens of milliohms for smaller cells. Why this is so interesting? Because as I said, impedance is a very information-rich measurement, and from these impedance curves, one can estimate the states of a battery, so state of charge, state of health, and internal temperature all relate in a let's say quantitative manner to impedance. But one can also be more sophisticated than that and use impedance measurement to identify what specific degradation modes are happening within a battery, and therefore also steer the operation of this battery in a way to minimize degradation. Last topic that is worth mentioning is that given that the impedance relates to internal temperature, this can also be used for early fault detection or early detection of thermal events such as thermal runaway, which is quite a fundamental issue in today's electric vehicles. Carrying out this is a method that is of course carried out very broadly in laboratories, and we see now an effort also to bring this into onboard systems on vehicles. There is not a let's say a standardized method to do so, of course, since this is still under work. But there are, let's say, I would say two main families of methods to achieve this. One is using some central power electronics to excite a battery, such as the high voltage inverter or the onboard charger, and then measure the current centrally and the cell voltages via the BMS analog front ends that are positioned as today. So the overall architecture of a battery to achieve this measurement is similar to today's architecture, which is a pro. A challenge of this is, of course, that in this case the current measurement is rather distant from the voltage and the voltage measurement of the cells, and to obtain a reliable impedance, these measurements needs to be synchronized, which is not a simple task, considering that these should be synchronized down to say about 10 or few tens of microseconds. So this for both current and voltage measurement is not a simple task to achieve. Another approach would be to have all needed measurements carried out locally. So by having electronics integrated or distributed in the battery system and eventually integrated at the level of each cell, where the advantage of this is, of course, that the proximity of the measurements to each cell simplifies the computation of impedance. The challenge to this is, of course, that it requires quite a high bill of material in terms of electronics that are integrated into a battery, and therefore the cost competitiveness of such a solution is challenging. But how all of this relates to current measurements? Well, at the basis, the impedance Z is voltage over current. So as for state of charge, also for impedance measurement, the current value is a fundamental input for carrying out EIS on board of vehicles. And in terms of what this will require to current sensors, it's a requirement that is primarily in terms of bandwidth, because typically impedance is measured up to 10 kilohertz, and this requires quite a high bandwidth in the battery current sensors. Normally, when state of charge computation was the primary or only function using current measurement, a sampling rate of 10 or 100 of milliseconds was enough. And now we are talking about microseconds for synchronization and sampling. So this is definitely a challenging requirement that we are working on. And the second topic of interest is that it's not yet very clear, I believe, what is the relation among the accuracy in the measurements of voltage and current, how this translates into the accuracy of the impedance estimate, and how the accuracy of the impedance estimate translates into an accuracy of the estimate of the applications, such as state of health or internal temperature. So all in all, it is expected that the accuracy will remain high, but it's very hard to quantify how this exactly relates to the application. So this is also something where I think there is a lot of work to be done. Finally, we've seen that measurement of impedance on board is quite a hot topic, but there is not a single solution yet. And as you saw, there is the possibility of carrying out this with a relatively more standard architecture, or with quite a disruptive distributed architecture. And depending on which of these approaches will prevail, different requirements might be needed for the measurement, either very tight synchronization and high bandwidth, or a very high degree of integration for distributed current measurements. And finally, the last topic I would like to touch is what we call battery drive fusion, or reconfigurable batteries. This is also a topic that I would like to add a personal comment, since I've worked on this also in my previous experience as a researcher. I think that this is a very fascinating and revolutionary topic, but is also such a change in architecture that is, I find, very challenging to motivate from a cost perspective. So I was actually quite surprised to see that OEMs are actively working on this at a quite consistent level. But to summarize what reconfigurable batteries means, it means in short a change in architecture where instead of having statically connected batteries or cells, these are assembled in small modules, and these modules are individually controlled via distributed power electronics. Then in such a way that the battery pack directly generates three-phase AC voltage. This is, I think, this image on the left is quite explicative in these terms. This is from a patent from Toyota, and actually just a few weeks ago, Stellantis showed or made public its plan to work on this kind of architecture for its future platforms. So the advantages of these are that some high voltage components are removed, such as the high voltage inverters, and that the individual control of these battery clusters allow for to optimize the usage of each of these of battery groups in terms of lifetime, safety, and also range. What are the implications of this for the measurements? One very maybe relatively trivial is that when this kind of architectures is employed, the state of charge of cells is not anymore just given by the integration of the current, but it also depends on the connection state of each individual cell. So in computation of state of charge, not only the accuracy of the measurement is very important, but also the timing of such measurement. And the second very important point is that current measurement in such an architecture is not used anymore just for let's say battery-centric applications such as state of charge estimation, but also for the control of these distributed electronics. And traditionally, battery applications have high requirements in accuracy. Power electronics have high requirements in bandwidth. So in this kind of architecture, these two requirements merge, constituting quite a challenge for measurement that have to be both accurate and quite fast. Yeah, so this is in a way similar to what is required for AES, accurate and quite fast measurements in terms of bandwidth, synchronization, and depending on where these measurements are carried out, also high integration into the battery systems. An approach we are working on to achieve these requirements of both accuracy and bandwidth is to work on sensor fusion techniques, where we use different technologies or channels with different characteristics, and by algorithmically merging these these different measurements, we aim at providing a resulting measurement that is both accurate and fast. So this is it for this topic. Just one last slide to wrap up. I've started my presentation introducing LEM as a whole, as a company, LEM provides electrical measurement solutions to support battery systems and all in all the electrification megatrend. New growing know-how within the company concerns ASIC development and the integration of more and more complex embedded software in the sensors we provide. Then when it comes to battery-specific products, the current sensors are quite important elements for battery systems, since they provide inputs for functions such as state of charge estimation. And we have a number of product lines, the CAB one being the best in class in terms of accuracy, and the HSTB one, HSTB V being the newest addition, and being based on open loop technology and magnetic offset compensation, which makes it quite accurate at a lower price point than the best-in-class CAB. When it comes to innovation plans in the battery domain, we've seen that there are quite a number of innovations taking place, also at a quite fast pace, that concerns battery state estimation, diagnostic, and also control and architecture. And we see that all of these still rely on high-performing current measurements, although in ways that are not necessarily the conventional way. So not only high accuracy, but also there are rising needs in terms of bandwidth and synchronization, as well as opportunities for higher integration of current sensors to satisfy these new functions and applications in these new architectures. So with this, I've concluded. Thank you again to the iBAT Association for giving me this, or giving to LEM this stage. And I'll be happy to answer your questions either now or in the coming days by email or call.
Thank you very much, Emil, for this very nice and exhaustive presentation. And we are now coming to the last part, which is basically the question and answer session. You all have been unmuted, so you can now switch on your microphone and talk. And I would simply ask you that you maybe raise your hand if you have a question, so that we can do that in a coordinated manner. Before starting the first questions from the audience, Emil, could you give us a little bit of an insight what is used today in the industry? Typically the more precise sensors, the CAB sensors, or is there a trend for this lower cost magnetic Hall effect sensors? What is the share typically? What are people that like these high voltage batteries with the, for instance, for LFP batteries, is there a trend that everybody uses this high accurate sensing technology also to get better estimates, or where do we go?
I'll bring back this slide. I think yes. I mean the CAB is still an extremely successful product, but there is also a clear push for lowering prices, which is the classical thing that always happens. And also, I think in the industry, let's say, I would say it like this: in the past years, there's been a kind of a scrambling to assemble very fast the first electric platforms. So the advantage of a product such as the CAB is that it is by its nature galvanically isolated, and it's you basically don't need to do much when implementing it. Just need to put it and connect it to the BMS. Now people are also becoming more expert and are working more and more on cost optimization. So expert maker also use shunts, which are which have their own challenges. They're not galvanically isolated per se, so they need to be they need some additional electronics. They are more sensitive to thermal effects, but they are also cheaper. And this is also, let's say, one of the reasons for us to work on this open loop technology that is cheaper than the FluxGate one, that is the CAB one, but with working into improving more and more the open loop technology, also based on software, on the embedded software that we can put on these devices, to be able to compete with a highly performing but cheap solution.
Okay, but do I interpret that correctly, that the only safety relevant sensor is the CAB, so with ASIL B and C, the others do not qualify yet for safety relevant operation?
Among these, yes, the newest family, the HSTBV, also is a functional safety. It's ASIL qualified.
Okay, thank you. Is there any questions from the audience? I see no hands rising. Is this linked to a technical problem that you cannot raise your hands? Can you speak? Is there anybody out there? Or do we interpret that there is no questions? I cannot see anything. And maybe simply, I take on. Is there any questions?
Was I so boring that everybody fell asleep?
I don't think so. There's still a lot of people that are here. I'm just not knowing if I did use this system correctly. Maybe could anybody try to speak up, unmute the microphone, and say something that we're at least knowing that you're still there?
I believe it works.
Okay, so everybody's still there. You could interact if you wish. There is just no questions so far. Okay. Okay, everything was clear then, Emil. I think that's the way you have to see it. Maybe one other question. I mean, it was, of course, very interesting to see that you're also working on this EIS and these integrated sensors, and the synchronization is, of course, an issue. I think you would need to get down to something like microseconds or even below if you want to go to 10 kilohertz.
Yeah, correct.
What is the current development status? Is there a product line that is in progress? Is there anything that you will announce soon? Is there anything that we could already try and test? Which TRL level are you now? Is there anything that you could reveal to us already now?
Let me think. I mean, LEM has a number of products already on the market that are battery specific, that are very accurate, but not at that level of bandwidth. And it has also a number of products that are more for power electronics applications that have very high bandwidth, but are not as accurate. So we are working on merging these two. I have been personally involved in a project based on this sensor fusion approach, where we try to merge the let's say the good qualities of two channels. This is at the level of prototype, yeah, I mean, this is, let's say, this is a very clear requirement, and we are working on different angles on this. I'm not able to point you right away in a product that would be the best one for reply right away, but I'm not probably the best person, since this would be a question for the product managers. I would also be happy to forward in case if you have a
it's just that we start to have clients that are interested in this not only accurate but also timely synchronized current acquisitions.
I mean, we've received a quite clear inputs in this respect, so this is quite a goal that we are working on.
Okay, perfect. So I would encourage all the participants again to have the last call for your questions. Now, is there anything that you would like to ask Emil right away? This doesn't seem to be the case, so you will have access to the presentation, you will see the presentation, and you also have Emil contact details. So if there is any questions that arise or that you want to ask in private, you know where to find Emil. Please do contact him by email or by phone as he offered. And with that, I would like again to thank you, Emil, for your presentation, and we will then officially conclude this Battery Tuesdays of today, with also many thanks to all the participants and your interest in our activities. Thank you very much. Looking forward to see you next time.
Thank you all.
Bye-bye.
Thank you, Andreas, and have a nice day. Bye.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Thank you very much. Bye-bye.